Swayam Prabha. Digital India. Educated India.
So the number of edges that you can create will be at most can be n. Yes, yes, but you can now, the next good. Yeah, but probably you're right in the sense that I do, like the number of edges I'll add is linear, but it's sort of, it is possible, like think of a fairly dense enough case that linear number of edges do create quite a lot of new cycles. So the cycle count might be large, but again that's not really the good measure. Yeah, the cycle resolution is like a finer analysis is worth thinking about. Far from. I think I'm being quite sloppy when I say it's like n square, it's polynomial. Yeah, it's, but yeah, worth thinking about what the, like, whether you can do it much more efficiently. Yeah. So here's sort of anecdotal evidence that at some point we are coding it up and just for our own sort of like playing around with it, and at some point we had some sort of bug that actually didn't look at all cycles, but even then it was quite successful for most of the time. Like even if we were just sampling to see cycles rather than doing like an entire DFS to find cycles, and even then like the allocations were turning out to be EF1. So it is likely that in particular for the number of say the shuffles that you have, number of cycles you have to resolve to go from one partial allocation to the other, especially in light of the fact that you're already starting with you're only assigning one new good and so on. So there's structure there worth figuring out. Yeah. Right, right. So it will save poly and so on. So I mean, yeah. So everything is poly, but yeah, a finer grained analysis is interesting. Okay, that's the algorithm. Here's the theorem statement. Let me see if I can use my trick again. Okay, so this is the theorem I want to prove, in particular prove by analyzing the algorithm. So essentially what I want to say is that the algorithm will always succeed, and hence not only find an allocation but in tandem prove the existence of EF1 allocations. Again, from a appreciative point of view, what's worthy to note here is that all of this, the entire existential guarantee, boils down to the fact that the acyclic graphs have a source vertex. It's almost a fairly immediate observation, but that with all this sort of steps built on it leads us to this entire theorem. So the total argument here, the guaranteed existence, is a consequence of that parity argument, the argument that acyclic graphs always admit a source. So I'll be a bit quick here because again, like most of it has been discussed multiple times. So running time is already observed, so this efficiently is fine. Note that to actually execute it, I just need to be able to figure out the NB graphs, right? So, and that entails polynomial queries to the valuations. So again, something that I'm not going to belabor too much, worth thinking about, that you can actually execute it even if you only had oracle access to the valuation. You only had access where you would submit a set and the oracle will tell you, for this agent the value of this set is blah. So even in that sort of model, even in that sort of adaptation of say the Robertson-Webb model, you can very easily execute this algorithm. And what I would want to prove is that the returned is EF1, by which I mean the final allocation, not the partial allocation, but once I have assigned all the goods, what I return, what the algorithm returns, is indeed EF1, and this is courtesy induction. So sort of the base case is when the algorithm starts, it's in fact NV free, everyone has an empty set, the NV graph is just a bunch of isolated vertices, this is fine. And now I'm going to say that consider the tth iteration of the while loop. So in this, I'm looking at this thing, the while loop, and as it executes, I stop it at the tth iteration, and then I'm going to analyze the fact that EF1 continues to hold. So by the inductive hypothesis, it held before this iteration. I just want to argue that it continues to hold after the iteration. So it's a proof by induction. So the superscript is now the timestamp t. So this is the partial allocation before the tth iteration. So this is EF1 by the inductive hypothesis. Now what happens is say with G so in this tth iteration, this specific good G gets assigned to this agent I. I'm just setting up notation here. Okay, so what does this mean? This means that the new partial allocation is going to be, so again, superscripts denote iteration count. So how does this bundle compare to this bundle? What is that? I mean, what's the connection? This is equal to this plus, what do I write next? I is the agent that receives this, G is the good that gets assigned. What is that? What is that? Union G, yeah. So that's it. And for every other agent, nothing stays the same. So, okay. So it's pretty much the thing that I've in fact had written up So I look at any other agent, I look at J. So there are two cases. So the first case is I'm considering J and I. So why do I have this inequality? What is special about I? So that's it, right? The I is a source vertex. This graph, so I picked I in the while loop because it was the source vertex, so I have this inequality. There was no, J was certainly, any J wasn't envious of I. So again, this is just the definition of what, how the bundle of I gets updated. So if I look at two agents that are, both of them are not equal to I, it's just EF1 property is already there and the bundles haven't changed. So this is directly by the induction hypothesis. And finally, the case of, I consider I and J, what I have is, this is by monotonicity. And the last inequality is because for J not equal to I, the set hasn't changed. So if it was EF1 to begin with, it will continue to be EF1, the choice of the good stays as is. These are like kind of, yeah, if you followed along the ideas, I'm just writing them in a precise formal manner. If it might look like a whole bunch of notation, but I guess if nothing else, through this you should be able to appreciate like this. It's just conveying those ideas in sort of in an equation form. Okay. Yeah, I cannot impress upon you the fact, the level of generality of this having having a result with this broad sort of this is too quite general. As computer scientists or as like looking at getting this sort of generic results is impressive, at least to me. So it's hard to find like non-trivial results with this such a broad scope. So this is an impressive result, and in a sort of a relative sense, the proof is quite direct. I mean, there are formal constructs here, but yeah, the ideas are kind of clean. So how much time do I have now? Okay, sure. So I have 15-20 minutes. Okay, I'll do one more result and then we'll kind of call it that. Yeah, so let's talk about, let's restrict ourselves to additive valuations. And actually, let me go back to the example and sort of remind you that specific example. So here it is in smaller font, here it is in bigger font. And so the valuations here are additive. We developed an algorithm that worked not just for additive, but in fact for monotone valuations. So certainly it does address this example. But now let me sort of come back and tell you that, look, I actually could have made your life easier. If I am sticking to additive valuations, there was in some sense there was a simpler algorithm that I could have discussed and called it a day. But I really did want to go over monotonic valuations. I did want to impress upon you the fact that EF1, these fair solutions exist in sort of vast levels of generality. Let's circle back to our example, circle back to the case of additive valuations and just sort of, spice things up, or say that, look, in some sense, I made you work a bit harder than required if additive valuations is all that you are interested in. And I'll give you a very simple algorithm to find EF1 allocations under the sort of limited range, under the limited class of additive valuation. So as we have seen, what good is a theorem if you don't have 2 or 3 proofs of it? So you can think of it as a second proof of existence in computation of EF1 allocations for under additive valuations. So the second theorem, if you will. So note that if I, again, this is in fact, it's just a corollary of the previous theorem, right? Additive valuations with non-negative values are monotonic, and hence I'm not actually giving you a so in that sense, this is, if I stop my theorem statement here, this is nothing new. You already have this as a consequence of the previous theorem. The differentiating feature is the method, the algorithm by which you can do this. What I'm trying to say here is that, look, there's actually a very natural algorithm when you are in the world of additive valuations. There's a very natural algorithm that achieves EF1. The algorithm is round robin. What I'll do is I will have the buffet of discrete indivisible goods on the table. I'll order every one of these n agents in some way. So just order them, say 1 through n. And I'll say, okay, please form a queue. Every agent comes to the buffet table of these indivisible items, picks exactly one of these indivisible items, say the item that it likes the most, and goes back to the end of the queue. So it's just a round robin method. I kind of go over these agents in a round robin fashion and let them select one, like the choice good, one after the other. So before the proof, I will actually So again, M is the set of unassigned goods that sort of keeps getting updated or reduced as the algorithm progresses. So I just keep running this for loop, right? So if at any point of time there's no good left, you stop the process. I mean, like the agents aren't there to stare at a blank table. So that's sort of the obvious condition. But say this is not the case, there's some good left unassigned, M is not empty. What you'll do is, so look at all the goods that are unassigned. So you're doing this argmax operation over the unassigned goods. Argmax means, well, you're just picking the good that achieves this maximum, and the good with the largest value. This is simply saying this is i's turn, so you're going in a round robin fashion. When i's turn comes in, I looks at the set of unassigned goods, M, among them picks the one that it values the most, the one that has maximum VIG, and that's it, pick, gets to select it. So what you do is you update, just add it, so AI has made a selection, and this get good is now off the table. You remove this good from your set M and you are good to go. That's it. The round robin executed with just this simple greedy choice. Again, this is not something I'll be able to substantiate in the interest of time. Round robin is a very interesting algorithm in the context of discrete fair division. The problems for which you would imagine that this thing won't work, something, again, let me throw a jargon here, something called submodular maximin fair division under submodular functions. Round robin, in fact, ends up being successful even then. There's a stronger solution concept called EFX. When the valuations are identical, a modification of round robin works. So if, say, at some point you are forced to design an algorithm for fair division of discrete indivisible goods and you are uninterested, a good heuristic to follow is the round robin method. So that's sort of, there's one takeaway, and at some point of time you actually do run into like doing things fairly. My sort of meta advice to you is try the round robin. Like this simple looking algorithm succeeds more often than not. And arguably this is a method that you would have, one has a natural appeal to it. Right. This is one of these cases where a simple algorithm actually ends up admitting a nice proof. Yeah, this is completely arbitrary. The ordering here among the agents does not matter. You can just shuffle them, so order the agents any which way you like. The algorithm is going to succeed. The only selection rule that you are following is when the agent gets to pick, when it's II's turn, it's the best, the most valued good for I that gets included in AI. No, I mean, you could have a case where you just, like everyone values something, there's no overlap. So it doesn't matter if you go before me or after me, you will end up there. Yeah, so there are three of us, there are three distinct goods. Yeah. So there are cases where there's just a unique EF1, so it doesn't matter. Okay, so that's the algorithm, and here's the proof of correctness. So I have M goods, and one after the other these M goods get selected. all I'm doing right now is again a notational setup. I'm just indexing them in the order they got selected. So G1 is the first good that got picked up. Note that what this means is at the first iteration, its I is equal to 1, it's agent 1's turn, and so agent 1 among all the goods picked G1. So based on this selection rule, you can be sure that for agent 1, G1 was the most valuable good. Right? Agent 1 has at its disposal the entire buffet, and he went after the dessert, picked this good G1. So eat your dessert first, I guess. So G1 is the first good that got selected. G2 is the second good. So agent 2 picks G2. Yada yada yada. Gn is the nth good that got selected. Now again, this is the indexing is the way the goods make an appearance in the algorithm. I look at the next good, Gn plus 1. Who owns this good? So this is the n plus 1th good that got selected as the algorithm proceeds. Who's the owner of this good? Agent 1, right? You have circled back and it's agent 1's turn to pick again and it picked it. So if I were to write it as a picture, A1 would look something like G1, A2, you have AI, so it's GI, AN plus AN is GN. Note that I am indexing them to exactly align in this crisp manner. That's just an indexing, right? I really don't care what the names or the identities are. I am just for notational convenience, I'm calling the good that got picked in the tth iteration GT, so on and so forth. So how many times will this algorithm iterate? What's the iteration count of this algorithm? M times, right? You just, every time one good goes out of contention, this G hat is kicked out, so it's M times. Right, so this is the first round of the round robin. Everyone picks one. You kind of go up and Gn plus 1 goes here. Right, it's the agent 1's turn again and she ends up picking this good, courtesy the indexing. This is Gn plus 2, this is G2n, right. So that's the second round of my round robin. It will kind of proceed till some point of time where Gm gets assigned and these guys sort of things stop. So note that a nice property that holds up front is that if you look at the difference of the cardinalities of any two subsets that have emerged, AI and AJ, they'll differ by at most 1. Right? In each round, everyone got 1. It might be the case that M is not divisible by N, so you'll have a tail hanging around. So there's a difference of 1, but okay, to begin with, at least in that sense, it's a fair partition. Like if you look at the count of things you have obtained, this is just plus minus 1 of any other person. That's a trivial observation, but okay, get things started. Right, the cardinalities are itself quite close. It's not like some guy is getting a very large number of goods versus some guy is getting a very fairly small number of goods. Again, a good instructive exercise once we finish this is to actually come up with examples where for additive valuations, if you execute the cycle resolution algorithm, you end up with a very different EF1 allocation versus round robin. Note that this cardinality property was no way guaranteed in the other one, where it is here. Again, if you are interested, I can tell you some useful properties that pop out of it. In particular, you can put this observation on steroids and get something like existence of EF1 under what are called matroids. Again, if you are interested, we can discuss this offline. That's just a passing remark to sort of ease you into what's happening. Fine, so this is what the partition looks like. I've indexed it so that things kind of match out cleanly. But here's the nice observation. So let's just so I start by looking at agent 1 and recall that very crucially that the valuations of all the agents are additive. So I start by considering agent 1, and my claim to you is that, you know what, this guy not only is satisfying EF1, agent 1 is NV free. Like he got to go first in every round, and that ensures that what he has obtained is quite good for agent 1. And the observation is that let's just do this argument round by round. Right, so let's just look at round 1. When I say round, I mean the one loop through all the agents. So I goes from 1 to n. Now if you want to be very pedantic, it's actually not for I equal to 1 to n. Okay, if I write this algorithm in a coding exam, why would I fail? I should get a hackathons would kill me out. Well, this would just run once, right? This will not return. A for loop, for I goes to 1 to n, it will terminate. So, yeah. Yeah, so, okay, slight abuse of notation, the agents are indexed 0 to n minus 1. So, yeah. What I said was morally correct. Figure it out. You guys are like, you can code, huh? You want me to do this, huh? Okay, here you go. Correct piece of pseudocode. You just do mod n. So it will keep circulating through all the agents 1 through n. Okay, so when I say a round, I mean like a sequence of n steps where from agent 1 to agent n, everyone picks a good. In this picture, this means this entire phase, like going from G1, G2 to Gn. So I look at round 1 and I note that if I have this, then this is at least V1 of Gi for all in fact, I don't even have to put this upper bound here, but let's say I do, just for be a bit more specific. Why do I have this inequality? Why can I say that G1 is valued the most by agent 1? Selection rule, right? Like agent 1 had the whole buffet, luxury of picking anything, went ahead and picked G1. So obviously like G1, which means that if I stop at this round, the agent has actually NV free, right? If I stopped right here when the first n goods are assigned, it's NV free, right? But it repeats, like look at this good, Gn plus 1, the same argument. All of these Gn plus 2 to G2n were assigned afterwards in later iterations, and hence like V1 of Gn plus t. So this is the good that one gets in round t is, yeah, I mean, let me just write it 1 for the second round. and this is round 2. Fine. So good by good, if you sort of go down this list, and agent 1 is quite happy. It was always getting to pick its first choice. This is exactly and the only place I'm going to use additivity. The fact that I have this good-wise comparison, additivity tells me that I can sum it up. The value that agent 1 has for this bundle is going to be never less than the set of goods that are assigned to any other agent. Because if I look at the round by round, agent 1 is doing quite well. So what I have is, so again focusing on agent 1, V1 of A1 is in fact V1 of AI for all agents I. I in fact have NV freeness. Right. My claim to you is that if I look at a pair of agents, say I and J, and I in fact comes before agent J, I'll never have NV. So in that sense, the NV here is only going to be upwards. It's only going to be towards someone that pushed you in the queue and went ahead in the round robin algorithm. Right. So, and my claim to you is that even then it remains EF1, even then you'll not sort of have NV beyond one good. And again, I think I'm enjoying this trick too much. Okay, so this is my allocation. Again, recollect the indexing. So now I'm like just going to sort of generalize it to any other agent and complete the proof. So, so pick any agent I, fix any agent I. Now, so here I have, this is going to be Gn plus I, G2n plus I, and so on. Again, courtesy my indexing. So note that it is possible that if I look at this point of time, if I look at AI, then I is envious of one of the agents whose index is smaller than I. Right. So it is possible. It's possible that like V of, so Gi is the good that agent I got to select in the first round of the round robin. It's possible that this is of value less than say G1, right? Possible, right? Because G1 is gone. By the time I came to the round robin buffet, one having nudged everyone was already up ahead, right? So fine, okay. But what's not going to ever happen is that this value is in fact less than the second good that agent 1 gets to pick. Gn plus 1 was selected in a later iteration. It was selected in a second round. So when I was about to select, Gn plus 1 was in the unassigned set capital M. So though we always have Vi of Gi, at least Vi of Gn plus I, n plus 1 in fact. So right, I'm trying to compare I and looking at a agent. For now I'm fixing 1, but you can repeat it for any agent whose index is smaller than I, right? So, but this will never happen because again it's a trivial selection rule. When I was about to select, why didn't it then not select Gn plus 1? Okay, but that's it. I mean the picture is that this is of value more than this will be of value more than like, so this is 2n plus 1, this is 3n plus 1, but you'll continue to have, So you might not be able to compare with the good in the same round, but you can compare to the good in this next round, in the round robin. So you have these comparisons. By this arrow, I mean the value is greater. It's not an NV edge, please. But again, the valuations are additive, which means if you sum it across, you are good to go. What's left is just one single good that actually made an appearance before you showed up. So if you look at AI, again, I am going to use the fact that once I have this good-wise comparison, I can sum it up, and that will give me this. There's at least Vi of, say, A1 minus G1. So it's not just NV free up to one good, it's NV free up to the good that was selected before you got to the round robin table. Right, so it's that very specific. In fact, it's always NV free with respect to the one of the first n goods that got assigned. So modulo that, you have this. So this I just argued with respect to A1, but what you have is for any agent j that with index smaller than I, which means j actually gets to go before I in every round in the round robin. What you have is, this is Vi Aj specifically Gj, the good that, so Aj is somewhere here, Gj is this good, and in the complementary case of goods after I, again we have already discussed, is in fact NV free. Not, forget EF1, it's legit NV free. So that's it. Yeah. It's sort of, you can think about like efficient data structures and such for doing it quite efficiently. Yeah, so again, you're doing this max exercise, it's like some sort of a heap and all would probably work. And as I said, like the allocation is quite balanced in terms of cardinality. It is robust, and this idea does translate into some other interesting settings. The fact that there is a specific ordering, there's a specific good, so on and so forth. So that kind of is a good property to notice. Bit. Right, so the number of pairs that have NV can be at most, like the person can NV, so like you might be the case that this is sort of there for all. So in the worst case, I do think there'll be, yeah. Right. So it's a hard problem. So I guess the question is, let's try to be a bit more, like set higher goals. So among possibly many EF1 allocation, find the one where the now NV is as between the pairs is minimized. So I mean the partition problem reduces to it. So if there is, for example, if there is an NV free, that's sort of equivalent to determining whether there is an NV free allocation, and that's a hard problem. But that's when it's 0. Yeah, so, okay. Here's a parting gift for you. So it's computationally hard to, I give you a discrete fair division instance, like a problem with additive valuation, n agents, m goods, determining if it admits a NV-free allocation is, this is an NP-hard problem, a fairly simple reduction. So if I tell you the problem, okay, try reducing partition to it. Okay, yeah, let's stop here. Thanks.